Right, good morning, everyone. This is, and welcome to the COVID-19 seminar. I am going to hand you over to Jan Hong Wu, who will introduce our speaker.
Thank you, Sarah. Thank you, Kevin, Dr. Bryan, and all the participants on behalf of Kumar, Dr. Moti at Fields Institute, and on behalf of the National Task Force on COVID Mathematics. We are very pleased to have another session of this seminar presented by Kevin. Kevin, Dr. Bryan is an assistant professor of strategic management at the University of Toronto Rotman School of Management and the lab economics. Economics is a creative destruction lab. He is applied game theorist who primarily study innovation, antitrust, knowledge diffusion, and he holds a PhD economics and strategy from Northwestern University. This is more of academic background. I like more of his own bio, talk about his interest and his all the experience. Let me read it, Kevin. So before entering academia, Kevin worked briefly at the U.S. Embassy in Beijing. Kevin, the embassy is still there, despite the current tension.
Yep.
For 2 years at the Federal Reserve. Kevin still has a copy of his memo on the housing bubbles and the real economy dated in February 2007. You can reprint it now. And for 2 days at the CIA and wonder what did you do down there. And for the too little time traveling to all the beautiful places you wanted to visit. My understanding, you have visited more than 120 countries and you continue to visit all of them. So with that, Kevin, so it's your time.
Great. Thank you very much, Chen Hong. So this paper, I think, might be somewhat unusual for the Fields Institute crowd. I apologize for the noise. The hazards of the COVID world is that there's a construction site that has decided to begin across the street from me this morning. So I think we should be okay with the mic, but let me know if not. So essentially what I'm gonna do here is I'm gonna walk through how we should think about the economic consequences of lockdowns or economic limits that we're putting in place due to COVID. And essentially we wanna be able to think about this in basically the most harmonized possible way. So if we want to consider, say, disease transmission, or we want to consider long-term health outcomes due to COVID across different sectors of the population, we essentially need to know how those sectors of the population are going to be affected by any economic shutdown, so we know essentially where to target ameliorative policies. So I'm just going to, pardon me just 1 second, I'm just going to get this plug back in here, and then we'll begin. So, in the, us economists, we're quite famous in our seminars for never letting each other speak. So suffice to say, you should feel free to interrupt if anything's not clear. I'm totally used to it, and I'll be glad to clear things up. So, okay, here's essentially the question we're gonna ask. If we reduce productivity in one sector, where productivity is just the dollar value of output per dollar value of inputs used, what are the consequences? So how might productivity be reduced? Well, let's imagine that because of COVID in the oil production sector, we restrict the number of employees that can be on site at one time. So with fewer employees on site, we're going to reduce the productivity of that sector, and it's going to directly harm the amount of oil we can produce at any given price. That's the direct effect. The indirect effects, though, can be quite large. So you might imagine, even if we don't restrict the pipeline sector at all, if I put economic restrictions due to COVID on the oil and gas sector, then of course the pipeline sector is going to pay more money for the oil they use or the gas they use, and that's going to harm their own productivity. And then as we go downstream from there, the trucking industry needs to use the gasoline that's refined after it comes out of the pipelines, which is produced after it comes from the oil and gas sector. So the trucking sector is going to face a productivity shock, even if we don't directly impose any restrictions on the trucking sector. And we can trace this all the way through the economy, all the way down to like the restaurant sector. If we open up the restaurants, but it's more expensive to get produce to the restaurants because the trucking sector's productivity is affected, because the pipeline sector is affected, because the oil and gas sector is affected, then that's going to harm productivity in the restaurant sector as well. What makes this even more challenging, of course, is that these can go in both ways. So the oil and gas sector is going to affect the trucking sector's productivity, but the same is true vice versa. If the trucking sector has a productivity shock, then that's going to affect how much we can produce in the oil and gas sector, because we need to be able to bring equipment, capital equipment, to the oil fields. Okay, so essentially, what we want to do is we want to think about how, if I drop productivity in industry X, driving price up and quantity down in that industry, that's going to make the inputs used by downstream industries more expensive. That's going to drop productivity downstream. And we'd like to be able to investigate this quantitatively, and even better, we'd like to be able to do it analytically, so that we can say give policymakers a dashboard or some type of tool that they can use interactively. So if we have to only do this through simulations, it's going to make it very difficult for us to give something that useful to policymakers. So luckily for us, there's an old technique. It goes back to the 1940s, really, 1950s, called input-output or production network economics. A guy named Vasily Leontiev won the Nobel Prize in 1973 for his work here. I'll walk you through the mathematics of how this works, and then we'll bring it to Canadian data. Let me give you a brief summary of what we're going to find. So essentially, we're going to take three parts. We're going to take an estimate of the productivity shock by sector. Essentially, how we're going to do this is we're going to take every sector of the economy, say publishing industries or trucking or whatever it happens to be. We're going to calculate what percentage of their workers are essential workers or are able to work from home. And we're going to assume that of all the remaining people, their productivity falls in half, okay, when we do a full lockdown. Then we're going to use Canadian government data on links across industries to see how a productivity shock in one sector is going to affect all the other sectors. We're going to throw that into this network model, this mathematical model we developed, and that will allow us to spit out estimated changes in employment or GDP by industry. Okay. The full model uses 54 sectors. So how small are these? You can think of these things like gas stations, publishing, truck transportation. That's roughly the size of the industries we're looking at. The estimates of who can work from home and who's essential, they're derived with slight modifications from estimates by other researchers based on Italy's lockdown in late February. And as I mentioned, the assumption will be that at peak lockdown, we have productivity for all non-work from home or essential workers. Okay, so how well does this work? It turns out that we don't have real-time employment data at the level of those 54 sectors. So every month, the Canadian government produces employment data at a slightly higher level of aggregation. So across the 16 sectors you see here, agriculture, forestry, utilities, et cetera. What I'm showing in this chart here is the second and third column. That's the GDP share and employment share of that industry in the Canadian economy. So agriculture is 1.5% of GDP, 1.8% of employment. The fourth column is the actual change in hours worked between February and April of this year. So in the construction sector, the number of hours worked fell 41%, 41.6%. In agriculture, fell 10.6%, et cetera. And the final column is when I aggregate across the smaller industries that make up each of these 16 industries, what the model is going to spit out as the change in hours worked between February and April when we went into the most extreme lockdown in Canada's case. And what you can see is, like, in relative terms, actually it matches really well. So the relative order of which industries face the largest decline in employment is essentially 1-to-1, right? So accommodation and food services is biggest, then information, culture, recreation, then construction, and so on down the line. Things like utilities or public administration, industries like ours are less affected. And the interesting thing about this, as you'll see when we run the model, is that this actually isn't obvious. So the direct changes to productivity in these industries have very little to do with the hours change that are coming out of the model. So about half of the change in hours is based on the direct productivity shocks of the direct lockdown. The other half of hours changed by industry is based on productivity harms to upstream industries that I'm trying to use, right? So if I look in the utility sector, for instance, we see in the true data, hours changed by 8.7%. In the model, they changed by about 10%. that's a sector that really faced very little in the way of legal restrictions on their ability to operate. So that drop in productivity in the utility sector is largely being driven by the fact that the utility sector requires the transportation sector and the manufacturing sector and other sectors in order to operate. Okay, and those sectors were affected by the lockdown. We can also use this model to investigate how we should reopen the economy, or if we went into, say, a second wave, what sectors of the economy we should close first. And the differences are pretty huge. So let me give you an example of two potential ways to start reopening the economy. Imagine when we were in April, we decided what we're going to do is we're only going to reopen the lockdown parts of upstream industries, say mining, manufacturing, transport, wholesale, okay? Or alternatively, we can first open up all the public-facing sectors, so retail, accommodations like hotels, restaurants, and bars, okay? So it turns out those two sets of industries are very similar in terms of their economic size in Canada. However, the equilibrium effects are super different. So if we fully reopen upstream, we get about 2.8 times, 280% the benefit to GDP and about 1.2x the benefit to employment versus opening public-facing sectors first. And the reason for that is if you allow me to open my restaurant, but you don't allow, for instance, the transportation sector to be fully open, it's hard for my restaurant to get the supplies I need to run the restaurant. It's going to be expensive. On the other hand, if I let the restaurants open, it doesn't really matter for the parts of the manufacturing sector that are still operating. They don't really use anything from the restaurant sector anyway. So that's essentially what's going to, that basic insight is essentially what's going to drive these differences. And you can see quantitatively, they're quite important. Okay, so let me just pause briefly. That's just a summary. Are there any questions before we go into the mathematical details of the model? Okay, perfect. And maybe I'll ask just Susan and Jinhong, if you, or sorry, Sarah and Jinhong, if you see a hand raised or something like that in Zoom. With my screen shared, I can't quite see it, so just feel free to call on anyone and let them know.
Yes, most participants are muted now. If they have any questions, they can raise the question or send me a message by chat, so I can convert to you and ask the person to raise the question directly.
Great, thank you very much. Okay, so let's walk through the model here. So again, this model goes back especially to Vasily Leontiev. I'm going to use a variant of it that comes from Long and Plosser in the 80s. This is like, I would say this is totally standard. I'll tell you what we're abstracting away from and how some more in-depth modern papers are going to try to get around some approximations I need to make. But I'll show you the kind of basic insight first. So we're going to describe an economy with n sectors, and we're going to assume that in every sector, firms are perfectly competitive. So what does that mean? When the economist says firms are perfectly competitive, we mean that all profits are competed away. So this has a number of useful properties in that we can treat the firm's revenue and the production, the kind of utility they give to society as the same. There's no kind of wedge between those two. We're going to use production in a so-called Cobb-Douglas form. So the Cobb-Douglas form says Y, which is production in sector I, depends on cap A in that sector. Cap A is the kind of overall productivity of the sectors. I think of this as just a multiplicative shock to how productive I am. L is the amount of labor I'm going to use as an input in my sector, so how much labor I hire. Alpha IL is just a parameter that'll come to in a second. And then the X's, Xij, is the amount of inputs I buy from sector J to produce in sector I. And again, alpha ij is just going to be a multiplicative or an exponential factor that I'll come to in a second. So essentially what the Cobb-Douglas form says is that the amount I can produce depends on how much labor I use, how much inputs from other sectors I use, what my productivity is, and these alpha factors, which are essentially in the production of this good. So imagine like restaurants, I need produce, I need labor, I need some real estate, I need electricity, et cetera, et cetera. So those alphas are representing how important each of those factors are for a given industry. The Cobb-Douglas form also has another nice property, which is that it's so-called constant returns to scale. So you can see here that if I were to double the amount of inputs I use, so double the amount of labor and double the amount of all inputs X, then I'm going to double the amount of output Y, right? Which is fairly sensible for a lot of industries. So it has some nice properties. One more property that we're going to come back to of this production function is that as prices change, when firms optimize, the share of spending, the share of input spending that they put on labor and on each X, on each input X, is going to stay constant. So if the price of some input goes up, I buy less of it. But if I was spending 10% of all my spending buying, say, electricity in the restaurant sector, if the price of electricity goes up, I buy less electricity, of course, but I still spend exactly 10% of my spending on electricity. So that this is an approximation that is going to rule out certain complementarities. So I'll come to that at the end of the talk. Just wanted you to be aware of it. In addition to the firm side, we're going to also have households. How are we going to model what consumers want to buy? We're going to use a so-called representative household. So the representative household here is going to supply labor. So we're just going to have one unit mass of labor that can be spread across firms. And they're going to consume from each industry an amount equal to C sub I, right? So the utility I get, U, from consumption is just going to sum up the log consumption I have from each industry, and I'm going to multiply that times a factor beta. Beta basically represents relatively how much do I want to consume from sector 1 versus sector 2 versus sector 3, okay? And you can see from these two equations, what the amount produced by any given sector only has two uses, right? It can either be used as an input to produce something else, or it can be consumed in final consumption by some consumer, okay? What are we going to look for? We're going to look for a so-called competitive equilibrium. What that means is I'm going to assume that demand equals supply. So for every industry, the amount I produce equals final consumption plus all the amount that's used as inputs for other industries. I'm going to assume that when all the firms are maximizing profits, when the consumer is maximizing their utility, I'm going to look for the vector of prices P and the wage W such that demand equals supply in every single industry when everyone's maximizing. And then what are we going to do with that competitive equilibrium? We're going to shock the productivity A, that vector of productivities for each sector, and we're going to let prices and wages regain equilibrium, and we're going to look at what happens to output in each industry. So if you're not familiar with these type of models, it turns out that we're, in addition to looking at output, we'll also look at employment. I'll come back to that in a second. It turns out that this model has an analytic solution. It's actually quite simple to solve for, as long as we make a first order approximation. How are we going to do that? We're going to use some matrix properties that are coming out of the firm profit maximization, plus a first order approximation, plus the Cobb-Douglas form, which, as I mentioned, has this nice property where the amount we spend on each sector remains a constant even as prices change. And that's going to allow us to see exactly what happens to production in each sector when I shock productivity, and therefore to employment in each sector when I shock productivity. Okay, so let's derive this. First, let me point out a few things. I'm going to keep the equation for production for each sector and consumer utility just at the top throughout the talk, just so we can refer to it as we go. So note that the total production, dollar value of production in each industry, so that's PI, the price of the good produced by industry I, times YI, the amount of output I produce in industry I. That's just going to be the dollar value of consumption plus the dollar value of use of my industry's outputs as inputs to other industries, okay? And we're going to use a couple of vectors. Let's call it Q and C. Q is just going to be the quantity produced vector, so PI times YI. And C is just going to be the dollar value of consumption vector for each industry, so PI times CI will be the rows. We need one more matrix. We're going to call it, for reasons I'll come to, the technical coefficient matrix. So this matrix T is one where entry ij is going to be equal to the amount of inputs that I use from industry I over the total amount of production I do. So this is going to be some number between 0 and 1, right? So if in the restaurant sector, 10% of what I'm using is coming from the electricity sector to produce food, then the technical coefficient matrix will have, for the entry at the restaurant cross electricity, is going to be 0.1, okay? Note we can do a nice little trick here. So the total quantity produced, the dollar value quantity produced, is just equal to the technical coefficient matrix times the total quantity produced plus final consumption, okay? We can take an inverse, and now we have this, this 1 minus t inverse matrix. We're gonna call this the Leontief inverse. We know the inverse exists because, as I mentioned, the technical coefficients are all between 0 and 1. Basically, I can't use more dollar value of some input than I produce if I'm maximizing profits. Okay, and so well, I know the spectral radius is less than 1, and everything is weakly positive, so I can invert this matrix. This Leontief matrix, this Leontief inverse, has a really intuitive property. Okay, so what's the property? Well, we know that the inverse times C, this is just equal to, another way to write it is the identity matrix times consumption plus the technical coefficients matrix times consumption plus the square of the technical coefficients matrix times consumption, and so on. So essentially, what is this saying? Well, intuitively, you might think we're like getting pretty close to the effect of a productivity shock on a given industry. So if you shock productivity in my industry, you might think, okay, there's some direct effect on my industry. Then there's the productivity shock of the things I use, proportional to how I use them, that's going to affect my industry. Then there's a productivity shock to the sectors that the sectors I use themselves use. And I'm going to trace through the relative proportions of how they come in, and so on and so on and so on. So that's essentially the intuition of why Leontief inverses are going to be related to productivity shocks. We'll derive it fully, but I think we're if you're following so far, we're basically 90% of the way there. Okay. So now let's take that Leontief matrix and link it to firm maximization of profits. So what are firms going to do in this world? If they maximize profits, profits are just the price I get for my good times how much I produce. Okay. Sorry, that should be YI, not XI. Minus the labor I use times the wage, minus how much of each input I use times the price of that input, right? So revenue minus cost, that's profit. If I substitute into that firm maximization problem, the production function there at the top for YI, then we can take first order conditions, and we get that the first order condition, the amount of input I use depends on this coefficient alpha that was just something we don't know, it's just something we're assuming theoretically for the moment, times the dollar value of how much I produce over the price of the thing that I'm using, and rearrange a little bit. And what you'll find is that alpha ij equals exactly that technical coefficient that we saw on the last page, right? So the technical coefficient was the dollar value of input I use from sector J to produce in sector I over the total production in sector I. And that's exactly what the alpha I is going to be. So this is how we're going to be able to link this theoretical term alpha to the data. Was there a question?
Not for me, but this is good.
Okay.
Thank you.
Perfect. Okay, so let's now take the first order conditions for labor and for each input, and we're going to substitute that into the production function yi there at the top, and then take logs. So I'll substitute them in, take logs after I divide by w, and what I see here now is essentially the log relative price of I is going to depend on the technical coefficient relating I and j times the log relative price of j, summing up over all of them, minus the productivity in sector I, minus some fixed factor some fixed factor phi that does not depend on anything we're going to let vary in this model. Okay, so we're just going to be able to ignore that when we consider changes. So therefore, if you look at now, convert this to matrix form, you know, what do we have? Well, we have the the log relative prices just equals, with one slight change here on the transpose, it just equals minus the Leontief inverse matrix times the log of productivity. Okay, so we can essentially, if I know the relative, if I know the Leontief inverse matrix, which again just comes from the data, okay, and you'll see where it comes from, and I know the productivity change, then I know how relative prices are going to change in each industry, right? And kind of intuitively, what's going to happen is that if you drop productivity in my sector, so prices are going to go up directly because productivity is lower. But if you drop productivity in my sector, I'm also going to harm other sectors. And if those other sectors I then use myself to produce, then my price is going to go up even more. So for example, in the manufacturing sector, I use a lot of other manufactured goods as an input. So productivity shock not only directly affects me, it also affects the productivity of other manufacturing firms directly, raising their prices, and hence affects my productivity once more indirectly, raising my prices a second time, right? All right, so we're getting quite close here. So now we know if I see a productivity shock and I have that technical coefficients matrix, I know how to get the relative price change. So now I need to figure out from a relative price change, what's going to happen to GDP and employment. So if I change the prices in relative prices in every industry, how much is employment going to fall? So we're going to use three equations here. The first one, yi equals ci plus the sum of xji. What does that say? That just says total output in sector I must equal total final consumption in sector I by consumers plus total use of what sector I produces by other industries. So it just says supply needs to equal demand. Okay. The second equation there, xij equals alpha ij dot dot dot. That was just the first order condition from profit maximization by firms for how much of each input they're going to use. And this last equation here, cj equals beta j times w over pj. If you look at the utility function there at the top of the screen on the right, this is just the first order condition from utility maximization for consumers. Okay, so we have supply equal demand, we have firms choose inputs optimally, we have consumers choose consumption optimally. Okay, put all those together, what do we have? We have that the dollar value of production in industry J is going to equal this beta J times the wage plus the technical coefficient factor summed up across industries times the dollar value of production in those industries that I'm using as an input. Okay, so how is this useful? Well, we can construct something called the Domar weight. So Domar is another economist who worked in the 1950s. Essentially, the Domar weight will define it as gross output in a given industry. So not final consumption, but just the price times how much I produce in that industry, divided by total production, total GDP. In this case, total production is just W the wage. Why is that? Well, we assume there's just a unit mass of labor. If there's a unit mass of labor, then all of the money they could possibly spend is just their wage W. And since there's only one representative consumer, that means total GDP, total final consumption in the economy can't be more than W, right? So the Domar weight lambda J is just going to be equal to gross output in a given industry divided by total GDP, which is just wage. And I can use the equation I derived on the previous page here to just substitute in for PJYJ. And now I've got that the Domar weight equals beta J plus the sum of technical coefficients times the Domar weight in other industries. So now I've got a nice circular equation. We know what to do in this case, right? Just write this in matrix form and solve. And I find that the matrix of Domar weights just equals the inverse, the Leontief inverse, 1 minus T inverse times beta, okay? So again, beta is kind of tough. We don't really know what beta is. That was just a theoretical object, how much consumers care about various industries. So don't worry, we're going to be able to get rid of this when we take things to data. I'll show you in a second. So I have this equation here for the Domar weights. And now what can I do? Well, I have two equations now that have Leontief inverses, right? I have this Domar weight equation. And then if I go back a few pages, I have this mapping, I have this log P over W, so log relative prices also relates to Leontief inverse and productivity, okay? So what am I gonna do here now? Well, I'm gonna use the fact that if I kind of point here, the total production over GDP, just the Domar weight, well, I know what PJ over W is gonna be in terms of the Leontief inverse. Now I know what PJ times YJ over W is in terms of the Leontief inverse. So all I need to do is just take logs and separate. So I'll have log PJ over W plus log YJ. I know what log PJ over W is in terms of the Leontief inverse. I know what log YJ now is. And so I can just solve. What do I find? I find that the log of output in each sector just equals the sum of the Leontief inverse coefficients times the log of productivity plus some fixed parameter theta. This is where the beta is going to wind up and some other things that are not going to vary. So this is great because now I want to look at, imagine I shock productivity. So I shock AJ. That's going to affect, that's not going to affect theta because theta doesn't depend on productivity A. So all I need to know to see what happens to final production is this Leontief inverse matrix, the size of the shock to A, and then I've got output. Okay, so this is essentially the full derivation of the production network approach. I'm omitting a few things. If I have time at the end, I'll discuss. Can we get around the first order approximations that I was taking in terms of maximization for the firm and the consumer? Can I get around the assumption of Cobb-Douglas form? So can I allow there to be complementarities across industries? And the reason that might matter is that you might think, okay, so if I shock the manufacturing sector, how does that affect the restaurant sector? Of course, we're already building in the ability for anything that the restaurant sector uses as a manufactured good. If that price goes up, it's bad for me as a restaurant. But you might also think that, for example, consumers care about complements between things. So I want to buy, if I have a car, I'll go to a restaurant. If I don't have a car, I won't go to a restaurant. And if I want those types of complementarities, then I can't use the Cobb-Douglas form. I need kind of a more general form for consumer preferences and for production, which are going to make things quite a bit more difficult. But it turns out I can still retain an analytic solution with a few assumptions. So I'll show you how to do that if we have time at the end of the talk. All right. So this is the end of the theory. So now let's take it to the data. We know what we need. We know we need this productivity shock, this matrix of productivity A. I know I need the Leontief inverse matrix, and then I can get, and I know I need the amount of production by industry that I start with. So then if I look at a percentage change in A for various sectors, I can find the percentage change in Y for those sectors. Okay, so how can we do this empirically? Let me just check the time and see where we are. Perfect. So I need two things. I need basically this input-output matrix, this matrix of technical coefficients, and I need final consumption. That's just going to come from some Canadian government data. And I need an estimate of the size of the productivity shock by industry. So the first one's straightforward. Every OECD country is going to publish something called the supply and use table. The most recent one for Canada is from 2015. Don't worry, like the relative use of each industry by other industries doesn't change that quickly. So we're basically fine using the 2015 data. For each of these 54 industries, I'll just extract how each industry is used by other industries from that government table. Number two takes a little bit of work. So when I do the Canadian lockdown in early April, late March, like what was the direct size in percentage terms of the productivity shock by industry, right? So who knows? So what I'm going to do, rather than try to calibrate on Canadian data, I'm going to take a non-Canadian estimate and just run the model and see how well we can match what happens in Canada. And as long as it matches pretty well, I'll feel confident using the model to make some predictions. So I'm going to use some data by Del Rio Chinona et al. essentially what they did was they took in Italy, they took every single job classifications, hundreds and hundreds of job classifications, and they looked at, is that job deemed essential by the Italian government, or can that job be done at home by work from home? And they assumed anything that's neither essential nor done from work from home in the most severe lockdown, those things have their productivity go to zero. So 30% of my workers in my sector can't work from home and aren't essential, then productivity in my sector is going to fall 30% based on the direct lockdown shock. So of course, in Canada, the precise composition of jobs in each industry isn't the same as Italy, but it's a sufficiently good approximation, I think, for policy. Okay. How well do these estimates work? So this is a paper by Neiman and Dingle. They looked at across countries their estimate before COVID of what percentage of jobs in that country could be done working from home. Then they looked at the share who shifted to work from home in surveys as of April after the COVID shock. And what you can see is the correlation is like super, super strong at the country level. There's some other measures of how well we were able to predict who can work from home. And this is just based on characteristics of the job. It works quite well, surprisingly well, actually. So for 44 of our 54 industries, I'm going to use exactly the Italian estimates for Canada. I'm just going to assume that our lockdown is only half as severe, which is just sounds about right. This is essentially the only calibrated parameter I'm using, this 50%. For 10 industries, I need to make some manual adjustments to how many workers are essential, largely due to just differences across countries. So for example, in Italy, the mining sector wasn't deemed essential. In Canada, I think every province allowed mining to remain open. Obviously, hugely different importance to the economies in Italy versus Canada. So if I just use the assumption that from the Italy data that all the mines were shut down, I get really crazy empirical results. So 44, we're just going to use directly the outside data, no attempt at calibration. 10 of the industries, I'll make some small modifications. I made them before I ran the model, incidentally. Okay, so what happens at the peak lockdown? So in April. Here I'm just showing you of the 54 sectors. I'm showing you the biggest ones just to make it visible on a slide. So I'm showing you everything with a GDP share of at least 1%. The second column is the size of the shock. So this says the direct shock in real estate was 25%. That means we assume that the government restrictions directly made real estate 25% less productive. The second and third column is the GDP share and employment share by industry. Generally, they're pretty close. So the employment share would be higher than the GDP share if I had a lot of low-wage workers in my industry. The employment share would be lower than the GDP share if I have a lot of high-wage workers. Or in the case of real estate, there's a really weird characteristic of how we compute GDP that if you own your house, the government is going to assume you're getting some housing services over time from owning your house, equivalent to if you'd rented it. And so the real estate sector includes basically 10% of GDP roughly is going to come from just the house that you own, which has no employment. So that's why there's such a big gap between GDP and employment there. The DOMAR weight here in the fourth column, this DOMAR weight, I didn't show you exactly how to derive this, but it turns out that the DOMAR weight can exactly say, if GDP in Canada falls 1% because of shock to your industry directly, the DOMAR weight is what percent does GDP overall fall once I trace the effects of that shock through other industries. So if you shock, say, food and beverage stores there at the bottom, you can see, 90% of the shock is just going to be the direct shock. 10% of the shock is going to be how food and beverage stores are used by other industries. On the other hand, manufacturing has a DOMAR weight of 4.4. So a shock to the manufacturing sector about, something almost 80% of the effect on the economy comes not from the direct restrictions on manufacturing, but from the fact that industries which use manufactured goods are now going to be worse off. So they're going to be less productive because they can't get the manufactured goods they need. All right. So employment DOMAR, think of this, I'm going to omit it just for the sake of time, but roughly it's, I'm thinking of the same thing. One job loss in this industry caused by a direct shock causes how many job losses in other industries indirectly. So you can see, like in oil and gas extraction, the GDP shock, there's such high wage workers in oil and gas that even though the GDP shock doesn't filter that much to other industries, like there's, every lost job in oil and gas is really consequential for other industries because a lost job is equivalent to like hundreds of thousands of dollars of production being lost. Okay. And this last column, change from shock, this is the estimate by each sector of at the peak lockdown, how much did production in that sector decline. And you can see in some like your food services and drinking places, we have, a 66% decline, truck transportation, 56%. And since we're assuming that wages are sticky, so production declines in your industry, employment declines at the same rate. Basically, we don't adjust wages. We just let people go temporarily. These numbers are equivalent to our estimated decline in hours worked by industry. So we're going to estimate, like in food service and drinking places, hours worked is going to fall 66% in the peak lockdown. Whereas in, say, credit intermediation, it falls, 6%. Utilities fall 6%. So quite different. This estimate matches the overall decline quite well. So between February and April in Canada, employment fell 27%, GDP fell 25%, and that's almost exactly what we're predicting in this model. I showed you this already that the employment drops by sector look pretty similar to what's in the Canadian government data at the level of aggregation they're able to give us. So what should we do with this? Well, we should think about how we can reopen. So I suggested in the opening that we really want to make sure that the upstream sectors are opening fully before we start opening things like restaurants and bars. Sometimes there's a justification for doing that, for opening upstream instead of restaurants and bars on the basis purely of public health. So you think, well, the restaurants and bars are going to have a lot of transmission of COVID, and so they should be the last thing we open. It turns out, even if that wasn't true, so even if restaurants are equally likely to be a vector for transmission of COVID compared to, say, oil and gas workers going back to work or manufacturing workers going back to work, even if those were equal, we should still open the upstream sectors first, because the restaurant sector will not be able to perform efficiently, even the parts we have open, the takeout food, if I shut down transportation, if I shut down manufacturing. Whereas the manufacturing sector can essentially perform fine if I keep all the restaurants working with just takeout food, okay? So what I show here is the effect if I were to open only the public-facing sectors. I would go from, I was at here a 24.7% GDP decline and a 27% employment decline. If I open the public-facing sectors, I'll still have a 21.7% GDP decline and a 20% employment decline. If, on the other hand, I open the upstream sectors first, okay? So I let manufacturing have everything open. I let wholesale trade, everything open, et cetera. Now I've only got a 16% drop in GDP and an 18.7% drop in employment. So we get much, much closer to where we were in February by opening these upstream sectors first. Okay, 2 more things, and then we'll take questions. So the most obvious extensions, I want to drop that Cobb-Douglas form, and I want to allow for second order and higher order effects when we look at firm and consumer optimization. Super active area of research right now. I gave you a few of the relevant sites. David Bucky, Fari, Mina, and Stock have a paper where they investigate these effects, including second order effects in the context of optimal policies for how the US should handle a second wave. I know some people trying to do this for UK data. Our goal with this paper was to give policymakers something useful in terms of how to think about the relative importance of industries as quick as possible. So we haven't done these full estimates. On the other hand, our model is, because it's just a matrix inversion, you can throw this on like a dashboard on a website and just let people play with opening various industries, which is pretty cool. I think for policymakers, that makes it a little easier to visualize what's going on. Okay. What can we, last thing, what can we do with this model? So how can we extend it to more useful cases than just the economy? So there are some papers like the Del Rio Chinona paper I mentioned, the Bucky paper. They're going to combine a production network approach to the economy with estimates about COVID transmission by sector to try to get at the kind of transmission weighted importance of opening each sector. We went a different way in our companion paper. We're going to look at the long run health consequences of income shocks in addition to just the income shock. So to essentially, if you lose your job, obviously you're worse off because you have less money. But it turns out, as we're already seeing in the data, depression goes up, suicide goes up, other negative long-term health consequences go up. And so you can look at, if we were to extend a lockdown in a certain way for a certain number of months, both what are the economic consequences, what are the distributional consequences, and what are the long-term health consequences given the distribution of people that work in various industries. I think my co-authors have mentioned this in the Ontario table, but the size they're not that small. So a lockdown of the size we had in March, April, if it continued for 3 to 6 months, we're talking many thousands of excess deaths due to the income loss related to the lockdown, not just COVID. So it's quantitatively quite important. The problem with these papers that combine, say, COVID transmission is that social distancing at work and in the economy, it's also endogenous to how much COVID there is. This Toxford paper discusses it. So effectively, the government can't choose as a parameter the extent of social distancing. And so it's just tough for me to think when it comes to government optimization, if I can't choose how much social distancing people do and how much the productivity shock is, if I think the level of COVID is high enough that people are endogenously changing, whether they're willing to go to work, then a model where I'm just letting the government choose these parameters probably doesn't make the most sense. Okay, I think that's all I've got. Really interested in any questions you have or any comments on where this can be taken, particularly given how interdisciplinary the crowd is. And thank you very much for having me.
Thank you, Kevin, very much for your very exciting presentation. And I know a group of people, at least my group, is working on this. So we are very excited to see how the economic consideration is playing a role now. You asked me this question before, but I can tell you we do have the transmission in different settings like school, household, community, and workforce. It would be very nice to have the information about the transmission in different economic sectors. Mm-hmm. That I don't know if you have this kind of information or not, but if you have, then I think that will really make the transmission model be the health model. Transmission model be a component of your economic model.
Yes, so that data, I know some people here are looking at it in the Canadian context. A lot of people are trying to do this with, say, like cell phone data, for example. I've seen pretty good estimates of this using US data. I don't have it for Canada, but I assume the sectors are similar enough that transmission probably looks similar at the sector level in say the US and Canada. So potentially that seems straightforward to graft on, I would think.
Great. So I have one person raised their hand. I think I have at least one expert in business continuity here. So Masoon, you raise your hand?
Yes. Mm-hmm.
Can you? Yeah. So you can ask a question directly.
Yeah. So then we have seen the main your assumption is the first order assumption, right?
Mm-hmm.
And we have seen that the Leontief inverse depend on the shock of the industry. And we have two kinds of industry during the COVID, the essential and non-essential industry.
Yep.
How do they have an impact for this? What is the dominated, supply shock or demand shock for the Leontief inverse?
Yeah, so there's no demand shock in this model at all, okay? So why is that? One is that you've probably seen the data. So personal income has not fallen. So government support in Canada, in the US, in the UK Germany has been very, very high. So normally I would think, okay, you lose your job, you don't have income. That's not been the case. Actually, personal income went up in the latest US data. I'm sure when we see the Q2 data in Canada, it's gone up as well. So to think through what the size of the demand shock is kind of tough. You might want to think, okay, if I think not just a demand shock based on my income being lower, but a demand shock based on I just don't want to go, right?
Yeah. Mm-hmm. Yeah.
So I think that's possible. I think we're probably fine doing what we do because the correlation between industries where they're not deemed essential and people can't work from home, and industries where no one's going to try to kind of use them, I would guess is very high, right? So like it's tough to think of like what would the industry be where they're allowed to work but no one's going to them in the context of like the April lockdown. I don't totally see what industry that would be. But yeah, potentially interesting. The other thing you mentioned was the first order approximation.
Yes.
So the first order approximation, the way it matters. So there are assumptions in the model where the Leontief inverse is giving me a globally accurate estimate. Okay, so I don't necessarily need first order approximations if I'm willing to make certain assumptions about what the production functions look like and what utility looks like for consumers. The first order approximation I would be worried about that quantitatively is probably on the order of, for the size of shock we're seeing, could easily be 10 to 20% changes in the kind of relative effects by industry. That's going to come from the fact that, we don't think that the only way that a productivity shock affects in some other industry affects me is by upstream industries. So I also think downstream, as you're thinking about, you probably have in mind, like, I shock the restaurant industry, they buy less produce, right? So if they buy less produce, like, then the shocks to productivity in restaurant must flow upstream to the agricultural sector. So the reason that doesn't happen is not the first order approximation in this setting, it's the Cobb-Douglas assumption. So the Cobb-Douglas assumption is that the amount, essentially the amount of spending I do on agriculture in the restaurant industry stays the same no matter what direct shock I get, right? So I just buy, if apples become more expensive, I buy less of them, but the amount I spend on them doesn't change. Mm-hmm. And so that assumption matters. I would look at the Baki, Farhi, Mina stock paper or Baki and Farhi Econometrica 2019. You can I'll send you a link if you give me an email, where they try to walk through how important it is. They think it's quite important. There's a little intellectual history here, actually. So there's a theorem called Halton's theorem, which you might be familiar with, which basically killed off any research on whether kind of heterogeneity across these industries matter for aggregate transmission of shocks. This paper is from like 1978. It's a really elegant paper. And the first order approximation in that paper plays a very important role. And people just didn't know how to solve these models in an analytic way without that assumption. Now we know how to do it with some papers starting in 2011. And so if you were interested in dropping the Cobb-Douglas assumption, dropping the first order approximation assumption, you can do it. But I just don't think, especially for a talk like this, I just don't think it's useful to kind of go into that until we've seen kind of how the most basic model works. And as you can see, like the basic model, like I have to say, like, I'm an economist, so we live in the world of theory, right? I'm a theoretical economist. And when we ran the model and I look, then, we were like, oh, hey, the May economic data from Canada came out. So we have sectoral employment drops. So let's see, like, how close did we come? And it's like, I don't know if I go back a few here, it's like, I mean, this to me is like, this is incredible. You know what I mean? Like this isn't a calibrated model. Like it turns out, like, knowing something about the relative importance of industry A for industry B, knowing those Domar weights essentially, really is very important for getting the effect of these productivity shocks, these lockdown shocks, correct. If we didn't have that, we'd have like completely different relative ranking of industries on how the lockdown affected them. And we would have predicted very poorly what happened in April to employment. So I think that even though there's a lot of approximations going on here, first order approximations, it doesn't do that bad. Like I feel comfortable using this to provide like basic advice that would be better than what the government's currently thinking in terms of how they should be open sectors.
Thank you.
Thank you, Kevin. Don't leave this page. Keep this page. So look at educational services. So how do you really calculate the GDP share and employment for educational services?
Oh yeah. So so how does the government calculate it? Not me.
Okay.
So,
Yeah.
Basically, there's a classification called NAICS, NAICS. So every country, really, not even just OECD country,
Right.
they're gonna do economic censuses, and in those censuses, we're going to basically classify every single worker and every dollar of final consumption by a sector. So the educational services sector is made up of like hundreds and hundreds and hundreds of smaller sectors, like university professor, first grade teacher, dot. And you just add up what percentage of Canadian employment in the latest data is in that sector. It's 7.5% of all the employment in Canada.
Right, but
so,
in that calculation, the upstream and downstream, I just don't see how when the school are not open. So it's not that the teacher are not going to work, but the kids are not going to school and the parents cannot go back to work.
Yeah. So this is important. So I think Sarah was mentioning this before we started, but super quantitatively important factor, not in this model, is sectors that affect other sectors not through being used as an economic input. So the two most important ones here, surely, are children's education and public transportation. Okay, so a lot of my workers need public transit to get to work. If I shut down public transit, some of them won't come to work. Okay?
Exactly.
A lot of my workers need someone to watch their kids. If I shut down the daycares, they can't come to work. Okay, and so that's not in the model because the reason is that in the government economic data in the supply and use tables, I don't know, like, in this sector, what fraction of workers don't, require daycare or don't have a great area. Like, presumably that's something we could compute and we can modify the model to incorporate those factors. I think that the data limits are going to be pretty binding. I could do some estimates. Like, I think the first thing I would do, I'd probably estimate, like, just based on the age distribution by sector, I would estimate what percentage of that sector are parents, and then I could get an estimate of how costly would it be to shut down schools. But I think it's a little bit beyond the ability of what we're trying to do here. My suspicion, like, so not from the data, is the same as yours, Jen Hong, is that it would be a disaster.
Probably not too much effect.
Yeah.
Well, it's probably that's both for the decision and also for the modeling purposes. So, so the data quality, if you do the estimation, could be a whole range.
Yeah. So you can think, like, educational services in this model, the only downstream sectors they affect are, like, if my corporation does some kind of corporate training, then I'm buying educational services as an input, right? So that's in the data. But the fact that my workers have kids in school, like, that's not in the data.
Right. And also found it strange when say it's educational services shut down very significantly, but it's not. That's because many of the university schools are not open, but the academic activities can continue. So I don't know what to mean by
So this is interesting. So let me go back. One here. Okay. So this was our estimates for the can I see education on here?
Yes, it's number 7.
Oh, there we are. Okay. Yeah. So the size of the direct shock was 15%. So essentially the estimates in the data were that 85% of people in the education sector were either essential or were working from home.
Oh, I see. Okay.
So
thank you.
So that's coming from Italy, right? That's not coming from us. That's just our estimate. But then when we plug that in to, the educational sector is using some other inputs that maybe are shut down, we come over here and we see, like, the overall estimated change from the shock was 19%, 19.9%. Okay. So that means, like, there are some people who, could have worked, but because of certain inputs that, like, I don't know, bus drivers need buses, they need the roads to be open, they need whatever happens to be. Then we had a little bit more of a drop in educational services. So the estimate of the model is that we see about a 20% decline in hours worked if we, at the peak of the lockdown in education. Not huge, right? So, I mean, nothing like food and beverages, right? You know, here at 66%.
Great, thank you. So are there other questions? I just want to mention that these socioeconomic consideration of reopening the economy or locking down is a top priority at least in the Ontario command table, and that's why we brought Kevin to the field seminar. We want to really know some of the mathematical details. Kevin presented this also to the Ontario table. And I think it is the intention of the Fields Institute and the task force that we want to organize some more in-depth brainstorm discussions. So when that happens, we will make an announcement. Thank you again, Kevin, for you coming to the Fields Institute. And I want to thank all of you for joining the seminar.
Yeah, thank you very much. Really appreciate it. And one last thing to mention, I think where these type of models I think will be useful. You know, back in March, things came to a halt so quickly we couldn't really be judicious. You know, if you look around the world, you know, look at say the southern U.S. or Spain or France or some parts of Australia, Israel, etc., that have had another wave. You know, now I think we know more on the health side and the economic side about the right way to balance economic restrictions and non-economic interventions to kind of limit transmission. So you know, there's hundreds and hundreds and hundreds of papers trying to look at this, and so I think you know the economic harms were so large in the shutdowns we did in March and April that more judicious selection, should we, for example, in Canada, should we happen to see another wave of COVID this fall, we should be able to avoid a lot of the economic harms, and as mentioned, the long-term consequences of those economic harms on things like suicide and drug abuse are not small. So we want to make sure that we get this right, and really appreciate all the work you guys are doing in the Ontario table, in addition to Fields is doing.
Thank you, Kevin. So again,
thank you very much.
Yeah.
And of course, send me an email if there's any paper you saw cited and you'd like information. I'm glad to share.
Fantastic. Yeah.
Bye, guys.